Okay, so page 10. And I don't know if you've forgotten, but this is I printed this from my website. This is the answer key to everything. So basically we're doing what's right in here. There's just a quick, sneaky peek at what's coming up. All right. Have I talked about the normal force? Okay. It's a really weird word. So, I think maybe I have. I just haven't used the term. So here's the normal force. If you have a box sitting on the ground, there's weight pushing it down, and then there's this other force pushing it up, and that's called the normal force. So far I've been just calling that the force of the ground pushing up, but technically there's a name for the force that's exerted between two surfaces. So normal force is a force exerted by a surface perpendicular to the surface. I'm hoping you all know what perpendicular means. So just in case you don't know what perpendicular means, it means at a right angle. So the normal force is never going to be like this or like this or like this. It's always going to be at a right angle to the surface. So this is going to be straight out. If you have a surface that's like this and you have a box sitting on this ramp, the ramp is going to push the box straight out with a normal force like that. And then weight would actually be in this direction. But we're not going to get into complicated things like that. All right, friction. Is friction more of a helpful force or an oppositional force? Can it ever be good? Yeah, when's it good? Right now. If there weren't any friction, what would potentially happen to you right now? You might slide out of your seat. If you imagine just your butt, you had little marbles underneath you. Every time you moved, your butt might slide out of your seat. And you wouldn't be able to leave the class. You'd stand up and your feet would just slip and you'd never be able to push yourself forward. So friction's not really a bad thing, but it is an oppositional force. It's a force that opposes surfaces sliding across one another. Okay. So the normal force, the reason I'm bringing that up is because it does relate to friction. So see my pencil right here? If I push it along, like it doesn't slide very well. This paper clip slides a little bit better than my pencil. I don't know. If I searched around for things, I could find some things that slide better than others. Does anybody know why? Why do some things have more friction than others? What did Orion? Yeah. So, that's a good one. So one thing that determines the strength of friction is roughness of surfaces. Has anybody ever seen sandpaper surface that's been stuck to steps or something? So that's to make it rougher. You get more traction and friction. But you could have a really smooth surface that's actually got a lot of friction. Can anybody think of an example of something smooth that rubs against something else that's smooth that actually has a lot of friction? I wouldn't say rocks. Generally, when I think of smooth rocks on smooth rocks, maybe. Orion? Car tire, what's it made of? Rubber. So materials like rubber actually have a lot of friction. So the type of material, rubber, Has anybody ever seen dragster tires? Dragster tires. Yeah, let's look at dragster tires. Somebody just mentioned not drag queen tires. I mean, they can have whatever kind of tires they want. Dragster tires. Dragster tires are really interesting. I'm just going to go to some images. Actually, no. Tempted to watch the YouTube video. Okay, here we go. This is a good picture of one. Yeah. Well, somebody was just mentioning car tires, and I thought I would bring these up. Do you see good tread on that? Do you think that there's a good amount of friction between dragster tires and the road? Well, shh. The whole point. Excuse me. Shh. If you want to do your whatever that is, just go back in this back and do it quietly. Yeah. So the whole point of a dragster, though, is to go as fast as possible. And wouldn't you think that the people who designed them would design them so they can push the road backward and make the road push the dragster forward? And they have. So here's how dragster tires work. First, they're made of rubber, which is kind of sticky. And second, before a race, does anybody know what they do? They do a burnout. And a few things happen. You can see some funny stuff happening, but they spin them, and when they spin them, they start to actually melt, and you get smoke. And that melted stuff sticks to the track, and then they back up, and then they've got A, sticky tires because they've halfway melted them, and B, they've got rubber on the track that their tires can stick to. And C, look at the amount of inflation here. Highly inflated or not inflated? Nah, it's and the reason for that is then they get more square inches of contact area with the road. So it's different than how with an ordinary car you would get traction. Ordinary cars, you have this tread pattern that'll allow you to stick to the road, but with a race car it's a little different because they're just burning their tires out constantly. You wouldn't want to have to pay to burn your tires out day after day after day. So what am I getting at? Back to, so type of material. If you were driving on ice and you had steel tires, it wouldn't work very well. Or if you had ice tires, that wouldn't work very well. So if you have tires with little studs in them, that's a different kind of thing. That's actually poking into the ice. It's sort of, I guess, making your tires rougher. So the third thing that determines friction that I mentioned before, but I want to see if you can answer it, is, yeah, so somebody already jumped forward. If you have a truck, Abby, if you're not quiet, I'm just going to send you out in the hall, and you can talk to other people in the hall. And Zoe too. So if you have tires where the roughness is not sufficient and the rubber is not sufficient and your tires are still slipping because you're on ice, then you can add weight. And specifically, it's not the weight that's important, it's the normal force. It's the normal force pushing on your tires from the road. So the normal force. I guess it is the weight too. Normal force of surfaces pushing against one another. Has anybody seen Karate Kid, the original? So if you need to warm up your hands, what can you do? You do this. Now if you do this and you go really fast, and what else do you need to do? I'm talking about Karate Kid. How do I warm up my hands with this? If my hands aren't warming enough, what do I do? What am I doing wrong? Push harder. So what is the force that's actually causing the warming? Friction. So there's friction between my hands, and the harder I push them together, the more friction there is. And friction doesn't necessarily produce motion, but it produces heat. And that's not something we're going to write in the notes, but that's where the energy goes when friction does its thing. Okay. So now a little practice problem, and then we're going to do some practice problems on the back, and then your homework is to do the rest of the practice problems. So this is a picture of a person's push. There's this mysterious force going upward. There's this one going downward. There's this one going backward. We're supposed to label all these. What's the name of this force? That's the weight of the box. What's this force? That's the normal force, which I just do F with an N subscript. And that would be how many newtons? 100 newtons. And what's this force? Friction. And I just remembered we haven't gone over that quiz. I'll have to do that next class. I'll give it back to you and go over it next class. It's okay. So we did A. Now we do B. Fill in the magnitude of the force that's missing. So we already did it. I did it for you. And calculate the net force acting on the box. Does anybody remember how to calculate the net force? We've done this kind of thing before. Net force equals what? So one way to do it is to do F equals ma, but we don't have an acceleration. What's the other way to find net force? Add them up. So let's add them all up. Let's add these two first. What do you get when you add those two? No, you get 0 because this is positive and this is negative. So yeah, those. Right. So because it's got an arrow downward, I wouldn't put in a sign. In fact, on some of your quizzes, I crossed out, you had a negative down here, and if you have an arrow that's going down, don't put a negative too, because it's just confusing. This is a downward 100, that's an upward 100, they cancel. So how much is the force? How many newtons? 20. 20 to which way? To the right. So the net force is positive 40 minus 20. So 40 minus 20 is 20 newtons rightward. Or you could just say positive 20 newtons. And now use Newton's second law to find the box's acceleration. Newton's second law, this is the thing Ava was saying earlier. So if I want to solve that for acceleration, can anybody tell me what the formula would be? Net force? Rightward, yeah. So, yeah, it's going to be net force divided by m. But you can always do this.
How do you find acceleration? I wish I would know.
So this is that formula, just with the algebra made easy. So if you cover up the A, the formula for acceleration is net force over mass. So it's net force, not EF. I know it looks like an E. That's just, if you're thinking it's EF, maybe for a little while, I should start writing F net over M, so people don't think that's EF. So the net force is 20 newtons, the mass is 10 kilograms, and the acceleration's 2 meters per second squared. So really what we're about to do, we've been doing this, except I feel like maybe we'll have to draw some extra stuff. I'm flipping. Flip. Ah, yeah. So the new thing here is there's no picture for you. You have to come up with a picture yourself. So draw your own pictures. So I'll read it. I'll draw a picture on the next one. You've got to draw your picture before I do. A 3-kilogram box is sliding with the velocity of negative 2 meters per second. So I'm going to draw my box over here. We can assume they're all on level surfaces. So this is 3 kilograms. And it's going to the left. But that's not a force, so I'm not going to draw that. Only forces go in my diagram. The force of friction acting on the block. That's not even a sentence. You know, maybe I'm supposed to tell you more. Maybe it's supposed to be find the force of friction acting on the block. The block's acceleration is positive 1 meter per second squared. I am going to write that. If the person's pushing on the block with a force of -4 newtons, what is the force of friction acting on the block? So this is the force of the push. Why did I draw the push going to the left? Because it's negative. Okay, so this part could have just been crossed out. We need to find the force of friction acting on the block. And I might as well draw the some other forces, although they're not really necessary. There's weight, which is how many newtons? 30. It's mass times g, so 30 newtons. There's the normal force, which is also going to be 30 newtons. And these are kind of irrelevant here. And what force am I missing? Friction. Which way is friction going? It's always the other way. If you push something to the left, or if it moves to the left, then friction is going to go to the right. So we need to find the force of friction. So we've got three tools. One is Newton's second law. One is weight equals mg, and then the third is net force equals the sum of all the forces. So all you really have to do is try to plug this stuff into one of these three formulas. Now this one, weight equals mg, that's kind of useless. That's a dead end. But let me see if I can do this. Net force equals the sum. So if I do that, I can say the net force equals this force plus the force of friction. Does that help me? Not really, because I don't know the net force. If I did, I could find the force of friction. So now I've got to use this. Net force equals ma. And the net force in this case is going to be the mass, 3 kilograms, times the acceleration, 1 meter per second squared, which equals 3 watts. What are the units for net force? Newtons. So now, does anybody have a suggestion? I know the net force. Yes, I can use this. So what I'm going to do, I'm just going to kind of be sneaky. I'm going to go back and get rid of, I'm just going to erase that, and I'm going to write 3 newtons there. Because that's the net force. I figured it out by doing mass times acceleration. 3 equals -4 plus this. So what should I do to solve for friction here? Add 4 to both sides. So if I add 4 to this side, I get friction. If I add 4 to that side, I get 7. So the force of friction is 7 newtons. And these were kind of useless. We really didn't need those two. We're going to need the weight formula in a little while. All right, see if you can do number 2. A child and her sled. They have a combined mass of 20 kilograms. I'll draw the child and her sled. Here's her sled. Here she is. I'll put a nice warm hat on her. But she's naked otherwise. No, she's wearing stick clothing. So in this one, we're looking for acceleration. Really? I don't think that the normal force and the weight play into this at all. Any of these problems on this page. They will on the next page. I'm going to come around and see if you have the answer, point to it.
I'm confused on how we have to draw the picture.
Practice drawing figures with all. Yeah, you're on good. Yep, that's good. You can. You're forces are good. So this is really exactly what we've done before, except it's easier, except that you're drawing your own diagram. That's it. The sign will tell you which direction. If you're having trouble getting answer yet, that's it.
I have all those.
You do? Let me see.
Oh, just in my head, not all negative.
Okay. Have one correct answer.
I guess I'm not.
Yeah, I don't understand this really.
That's just what it's just the force. This is the force.
I got it.
You got it.
I did? Let's go.
And Ray just said, oh.
So.
Anybody else want me to check yours?
I'm very impressed with myself.
Okay, so we got a handful of correct answers, but most people didn't get it. It's okay. So here's how to do it. First, draw all the forces we know of. Some of these forces are useless. I'm just going to draw them anyway. Here's a useless one because it doesn't affect the net force here. The weight is 200 newtons. And then it's useless because these cancel out. The normal force is also 200 newtons. But I'd like you to get in the habit of being able to draw them. The important forces are this force. This is the push force. And it's positive 40, which means it's like this. So you could call it, I'm just going to call it the push. Normally I would write F with a little subscript push, but I'm just showing you can really label these whatever you want as long as it makes sense. So 40 newtons to the right, and then the other force, negative 10, this is 10 newtons, and this is the force of friction. So really, I only need two things here. I only need to know that that F equals ma. That's Newton's second law. That's the big one. And then I need to know that the net force is the sum of all these. So what I'm going to do first is find the net force by adding them all up. This plus this is 0. So I can leave those out. This is positive 40. This is negative 10. What's 40 minus 10? 30. So it's the net force is 30 newtons. Now, according to Newton's second law, F equals ma. If the net force equals ma, then what does A equal? Yeah. So I'll write it up at the top again, just for any of you who don't want to do the
I have a question.
algebra. Hold on. If I want to find acceleration, cover that up. It's net force over m. And then I'll answer your question in just a second. But let me just finish this for some resolution. So the net force is 30. I figured that out by adding everything up. And the mass is 20. And 30 divided by 20 is 1.5. So that's the final answer. That's the acceleration. What's your question, Abby?
Yeah, so my question is, how did you get to 100?
Weight equals mass times g, and g is 10.
Okay.
All right. So your homework is to do 3 and 4. And if you need to look at my answers, look at my answers, but don't look at them before you do it. Try it first and then look at my answers.